So, indeed, I would like to repeat Dirk's comment about what a pleasure it is to see so many of my friends together again for the first time in a long, long time. I'm going to give a lecture which, well, of course, this room is filled with experts. And as a result, one hesitates to speak about things that they know and have known for years and probably, in many cases, know better than I do. But there are also here some non-experts. So I'm going to try to give, for today, Teichmüller spaces two big examples of the Thurston pullback map. The skinning map, and the pullback map. For post-critically finite. Branch. And if I get through that in 50 minutes, that won't be doing so badly. So, Teichmüller spaces. Let S be a Riemann surface. In the actual applications of Thurston's theorem, the Teichmüller spaces are only Teichmüller spaces of Riemann surfaces of finite type, complements of finitely many points in a compact Riemann surface. But I think that in the context of this conference, it is a much better idea to give the general definition which applies to any Riemann surface, because trying to generalize Thurston's theorems to more general settings, such as, for instance, transcendental functions, is going to require looking at Riemann surfaces of infinite type. And probably it's a good idea to give the definition in that generality, in addition to which it's not all that much harder. So let S be a Riemann surface, but you ought to be thinking something like P1 minus an infinite set. An infinite set of points, or something like that. With say, finitely many accumulation points. Or perhaps accumulating in a simple closed curve. Or there are many other possibilities. Teichmüller space modeled on S is equal to the set of phi from S to X, quasi-conformal homeomorphism with X a Riemann surface S phi a quasi-conformal homeomorphism up to an equivalence relation. And the equivalence relation is if you have S, x1, phi 1, x2, phi 2, x1, phi 1 is equivalent to x2, phi 2, if and only if there exists f from x1 to x2 analytic isomorphism such that first phi 1 and then f is, and now there's a hesitation as to whether one wants to write isotopic or homotopic. And it's a theorem, but not a trivial theorem, that they're equivalent. So I will write isotopic to phi 2, but this could be just homotopic. And it is a theorem of surface topology, but not an easy one, that those two notions, that those two are equivalent. Now, what kinds of structures, this is just a point set. What kinds of structures does it have? Teichmüller space sub S is a Banach analytic manifold. Of course, finite dimensional if S is a finite type. And it is a metric space. Actually, it's a metric space in lots of different ways. And there are people who are fond of different metrics on the Teichmüller space. But I have my favorite. It is the Teichmüller metric. And that's the one that is relevant to all applications that I know of Teichmüller theory. Well, that isn't quite true. It turns out that the Peterson-Weil metric is also relevant to some aspects, but I will not be speaking of that one. The Banach analytic structure I'm going to temporarily ignore. Could you speak louder? Analytic isomorphism. At least for Riemann surfaces of finite type, you should think that there is analytic data, the complex structure of the Riemann surface, and combinatorial data, the marking phi. It isn't quite true that the marking is just combinatorial, but it is just combinatorial in the case of Riemann surfaces of finite type. Now let me the metric. The metric is sort of an obvious one. The distance between x1 phi1 and x2 phi2 is equal to the infimum of log k of f, where it's the same drawing as before. S, x1, x2, f, phi1, phi2, f, quasi-conformal homeomorphism, such that first phi1 and then f is isotopic to phi2. And the point about this quasi-conformal homeomorphism is that a quasi-conformal homeomorphism of quasi-conformal dilatation f, k equals 1, is in fact analytic. And therefore, if the distance of 2 points of Teichmuller space is 0, they do in fact coincide. It's the very definition of the equivalence relation. This word quasi-conformal is essential for the present purposes, but it could just be a homeomorphism as if we were in surfaces of finite type. But it's important to realize, at least for this conference, that if, well, P1 minus a sequence converging to a point x infinity, that does not correspond to just one Teichmuller space. It has one topological model, but it corresponds to uncountably different topological Teichmuller spaces. The reason for that is theorem. If gamma is a curve on S and tau maps to length sub tau of gamma, associates to x phi in Teichmuller space of S, the geodesic on x homotopic to phi of gamma, then log of L gamma, L sub tau of gamma, well, tau maps to the logarithm, is Lipschitz of ratio 1. So now, if you have a sequence accumulating to a point, you can look, for instance, at these curves. Each one has a length and a log length, and they form a sequence of numbers. And those sequences of numbers for two different Riemann surfaces in the same Teichmüller space the logarithms of the lengths have to belong to little L infinity, has to be a bounded sequence. As a result, but those sequences can be anything you like. And so there are huge numbers of Teichmüller spaces modeled on that topology. They somehow look like little L infinity over little L1. And that's a bizarre space, little L infinity, which is some non-separable Banach space divided by little L1, the set of summable series. It's a strange, highly non-Hausdorff space and so forth. And this is designed to make you realize that you can't just loosely talk about Teichmüller spaces of infinite type Riemann surfaces without being really careful about what you're doing, that these Teichmüller spaces are really different. Let me see. This one, that isn't the one I want. This one. Okay. Let me say one more generality about Teichmüller space. And this is really the only way in which I am going to use the complex structure. The tangent space at tau, the Teichmüller space based on S, is the dual of Q1 of X. The space of integrable holomorphic quadratic differentials. On X. So a quadratic differential is something which in local coordinates, a quadratic differential is written Q is equal to alpha of Z dz squared, and then absolute value of Q is equal to absolute value of alpha of Z dx dy. And so norm of Q, L1 norm of Q, is equal to the integral of this norm of Q over X, which is the norm of Q is the absolute value of Q is naturally a measure, which you should think of as the area. And so these are the quadratic differentials of finite area. And there's much to say about trying to understand the geometry of quadratic differentials. Understanding in detail the geometry of quadratic differentials is essential to understanding Thurston's theorems. But just at the moment, I'm going to leave it at that. Okay, so this is my introduction to Teichmüller theory, and this is where I ask for questions. You're supposed to understand every word I have written. This is not supposed to be mysterious, and if you don't, now is the time to speak up.
The word here from the back is maybe very spirit of attention, not only within the lecture, but as much as possible. Sometimes ask that question. You need to give it.
Okay, I did not get a single question, which makes me wonder whether I'm talking into a void or not. But well, it's to give you an idea as to what you might have an infinite set with an infinite accumulation
If
set.
I remove a Cantor set, it's especially bad.
It's worse than a set with an accumulation point. But the answer is, yeah, trying to understand the multiplicity of possible possible Teichmüller spaces modeled on P1 minus a Cantor set is well, it's one of these many things that you can try to understand. They're probably highly relevant. It could be any closed set, but specifically a sequence going, a countable set accumulating on finitely many points is sort of the next step in understanding Teichmüller theory for transcendental functions. Well, Thurston theory for transcendental functions. That's the example that I'm trying to understand at the moment. And I think there are already, in that setting, a myriad difficult problems. Okay, so this is my introduction to Teichmüller theory. I'm going to use the language and the words that were used here constantly. Oh, I'd like to point out a little bit. In the setting of infinite dimensional Teichmüller spaces, Teichmüller space is not modeled on a separable Riemann surface, so it is not a reflective Riemann, a reflective Banach space. The dual of it is true that the tangent space is the dual of the holomorphic one forms, but it is not true that the holomorphic one forms are the dual of the tangent space, except for finite dimensional, in the finite dimensional setting. I mentioned that when thinking about the topology of even these Teichmüller spaces, you have to think about little L infinity. And little L infinity is not a separable Banach space. So you cannot expect that these are the kinds of spaces where duality, you just say, oh yes, the dual of the dual and so forth. The dual of the dual is not the space you started out with. Oh, and there's one more thing that I really ought to say. This gives you a metric on the tangent space, the dual metric of the L1 metric on the quadratic differentials. And when you have a metric on the tangent, a norm on the tangent space, you automatically get a metric on the space itself. The metric on Teichmüller space sub S is the metric associated to the infinitesimal metric on the tangent bundle of Teichmüller space dual to the L1 norm on Q1 of x. It is true that the distance that it comes from knowing the lengths of tangent vectors is that log k of f. There might be a factor of 1/2 depending on normalizations. I believe that this last statement is due to Richard Hamilton. I'm not really sure. Maybe just as one more word. It's all very well to talk about Q1 of x. Even in the finite case, the norm on Q1 of x is a really entertaining object. There you have this finite dimensional Q1 of x, and there you have the unit ball of its norm, and you might sort of imagine running your hand over this unit ball and feeling how bumpy it is. And its bumpiness, as it turns out, reflects the geometry of the underlying Riemann surface. The Himalayas are running along there, the bumpiest spot, giving you a picture of the underlying Riemann surface. It's something which was developed mainly by Royden many years ago, and which I've spent my life looking at this unit ball in the space of quadratic differentials. It's an exciting space in itself. This Banach, a finite dimensional Banach space, isn't just, oh yes, a Banach, all norms are equivalent. The details of the norm really matter. Come on. You're going to go all the way up, and how do I get the other one to come down? I hope it's like this. Yes. Okay. Maybe considering the audience that is here, I will start out with the skinning map, which probably you don't know as well as the Thurston pullback map, but it's a most entertaining map. Suppose gamma in PSL2C is a finitely generated discrete group. That's called the Kleinian group. It is then a great theorem of Alfors. Oh, then it is true that P1, which I will write of as the boundary of H3. Of course, H3 is a complete metric space, so it doesn't really quite have a boundary. But there are many models of the hyperbolic space. There's the ball model, there's the upper half space model, there's a hyperboloid model, there are many models, but it is absolutely true that the set of ends of geodesics is naturally the Riemann sphere. It is naturally it has a natural complex structure. It doesn't have a natural metric, but it does have a natural complex structure. And every automorphism of H3 extends as an automorphism of its boundary, although the words automorphism mean different things in that sentence. In one case, it's a set of isometries, and in the other case, it's a set of analytic isomorphisms. P1 doesn't have a natural metric, but it does have, of course, a natural complex structure. Then Alfors proved, P1 is equal to the limit set of gamma disjoint union, the regular set of gamma, limit set, regular set. Which you should think of as just like dividing the Riemann sphere into the Julia set and the Fatou set. And in fact, part of the purpose of this conference is to bring out the similarities of those two notions. This is the set of all gamma. This is equal to P1 inter gamma x for any x in H3. It's a set of accumulations, and you should think of this as very analogous to the closure of the set of inverse images of any point. Laurent, speak louder. You are absolutely right. I want to write the closure. You could also take x in P1 except for some exceptional cases. And lambda gamma is compact. So omega gamma is open. And Alfors proved that omega gamma over gamma is a finite union of Riemann surfaces of finite type. This theorem is the other side of the Sullivan dictionary. On the other side of the Sullivan dictionary, you have the no wandering theorem, no wandering domains theorem. it turns out that the proofs are almost identical. The proof of the no-wandering domains theorem and the proof of the Alforce finiteness theorem are almost identical. And this is perhaps the main entry, and certainly the inspiring entry of the Sullivan Dictionary. Let us suppose that H3 over gamma is geometrically finite. And that is something that is going, I am not able to explain that word right now, though, oh well, I guess I sort of could. It has a finite-sided fundamental domain, a finite-sided Dirichlet fundamental domain. And the stabilizer of each component of omega gamma is quasi-Fuchsian. A quasi-conformal conjugate of a Fuchsian group. But it's easy to say quasi-Fuchsian, but I'd like to emphasize that quasi-Fuchsian groups have a world of geometry, and you can't just dismiss this definition as being fully explanatory. So here is an attempt of drawing what this group looks like. Here is hyperbolic space, or perhaps rather its boundary. H3 inside here, P1 here. Here is omega gamma. Here is the quotient. This is P1 over gamma, which, excuse me, this is omega gamma over gamma, a finite union of Riemann surfaces of finite type. And for each component, you have a universal covering space of that, of of that which I would call a leopard spot to the corresponding Riemann surface. So this is my picture of the setup of the Thurston's hyperbolization theorem for Haken manifolds. You then have the following rather extraordinary construction. Yes? They're quasi-disks. They're quasi-disks because I have put in to my hypothesis that the stabilizers of the components are quasi-Fuchsian. Excuse me?
That's a strong restriction. There could exist examples.
Oh, there are lots of other possibilities, but that's the restriction that I'm working under. You then have the following extraordinary construction. If you choose some particular one of these components, say this one, S1, S1, that particular spot, spot 1, you can look at H3 divided by the stabilizer of that spot. And what does it look like? On one side, you see exactly the green Riemann surface. And then you see a Riemann surface. And what's on the other side? And what's on the other side? Well, the other side corresponds to the whole outside of S1 divided by your quasi-Fuchsian group. And in particular, it has all the structure of all these spots. So it contains, it's also a Riemann surface of genus 3 as I have drawn it, but it has a whole extraordinary structure. I don't agree. 10 minutes. I don't agree. 10 minutes. 10 minutes. I started, and it isn't my fault, 5 minutes late. And I do want to get to the second spot here. Now, supposing that I take a point tau in Teichmüller space of this particular spot. That's a finite dimensional Teichmüller space. Well, actually, in Teichmüller space of omega gamma over gamma. So that's the product of the Teichmüller spaces for all these things. That gives a complex structure in every spot. It gives a complex structure on all of these Riemann surfaces. Therefore, it gives a complex structure on all these spots. But with the hypothesis that the group is geometrically finite, the limit set has measure 0, and so it's actually a complex structure on the whole remainder of the whole remainder of the sphere. And so it gives a complex structure on all these spots, except that here there's no good reason to believe that the spots are simply connected, and therefore it gives a complex structure to this surface. And this defines, taking the complex structure on here and looking at the mirror surface, the other side, the wild surfaces on the other side, gives you a map sigma sub x naught, or sigma sub gamma perhaps, from Teichmüller space of omega gamma over gamma to Teichmüller space of omega gamma over gamma star, the complex conjugate surface. This is the wildest map you've ever heard of. And this is the basic construction of Thurston's hyperbolization theory. So I'm starting with a complex structure on each of these surfaces. I'm lifting it to a complex structure on each spot. That gives me a complex structure on the Riemann sphere, because the complement has measure 0. I'm then dividing it out by the stabilizer of one spot. Of course, the division of the stabilizer of that one spot is just the complex structure of that spot. But dividing out the outside by the group gives you some completely different complex structure on the conjugate surface. You could do this for each one of these surfaces, and you get new complex structures on the conjugate surface. Corresponding to the spotted and striped structure of these surfaces. And if you understand even just this from today, you're already doing reasonably well. This map is the fundamental object in the construction of Thurston's hyperbolization theorems. The skinning map. The derivative at tau of the sigma sub gamma transpose associated to a quadratic differential. What does it do? It takes a quadratic differential on each of these Riemann surfaces, lifts it to all the spots, then pushes it forward from all the spots to all of these Riemann surfaces, giving you, in the final analysis, a quadratic differential on all those surfaces. And the proof of Thurston's theorem consists of showing that this operator has norm less than 1, with the norm depending only on the length of the shortest curve, shortest geodesic for the complex structure tau. This is an immensely hard theorem. The proof of Thurston's theorem, 90% of the difficulty is showing the norm of d tau sigma gamma transpose is less than 1 by a constant depending only on the position of tau in moduli space. Proof of Teichmüller's theorem, of Thurston's theorem. Unfortunately, this is extremely difficult to prove. It is true, but it's just not obvious. Now, what is your time?
It's
9:57, so I'm going to have to stop here, huh?
Yeah.
Okay, well, I'm going to stop here. I'm afraid I was sketchy at the end, and I never got to the second entry of my plan.
So I think we have time for some very quick question. If not, there is a little break now, and we can discuss in the lobby, but there's time for some questions.
Please remember that I'm a little deaf, and if you want to ask a question, you have to speak loud.
I can use the microphone.
The image is bounded of this map.
So I believe, well, I do not understand the bounded image theorem. I don't know how to prove it, but I do know how to prove this statement. I do know how to prove that statement, but I do not know how to prove the bounded image theorem. And I hope that the bounded image theorem actually is a theorem, but well, I don't know a proof. Well, it is obvious, or almost obvious, that the direct image operator always has norm. Well, it's really obvious, it's a generality, that the direct image operator has norm less than or equal to 1. In this case, it is essentially obvious that it has norm less than 1 at every point. On the other hand, what is really difficult is showing that that norm depends only on the position of Teichmüller space, of tau in moduli space. If it certainly is true, if it maps, but for one thing, it isn't true. For one thing, it isn't true because there's a hypothesis to show that that norm is less than 1, which is that there are no embedded annuli that there are no annuli. Let me try to draw you a candidate annulus. That there is a closed curve contained in one image of a spot, but that image of the spot then is not simply connected, and I call it a stripe. And then that curve bounds also is one boundary curve of an annulus inside the inside this three-dimensional quotient. Well, it's really a handle body. It's a structure between. It's something which is, well, it isn't a handle body. It's a surface cross 0, 1. And in order to have the norm of this operator be less than 1, it is necessary that there be no such things. And therefore, the proper image theorem has to depend on the hypothesis that these annuli do not exist. I think as much as I can answer your question right now, that's my answer. Under that hypothesis, the contraction is uniform, yes.
Are there any more questions? Well, I guess it's due to say that for any detail and much, much, much more, I refer you to the 3 books of the speaker, right? Exactly on the Teichmuller theory and applications.
There are some questions by Michael Huschenko in the chat.
Yes, so maybe this is true. We should check whether there are any questions from the remote participants. No? Nothing.
So who's speaking? Let me see. I'm very pleased to see.
You should look at there so that they see you.
But he wants to see who's.
Okay.
There are some questions in the chat.
So I have a lot of friends
The
there.
spots are discs on the sphere,
I
I
see
think.
Sean, I see Raluca, I see Remus, I see Lasse, I see Sabia. Lots and lots of good friends of mine. Hello, Pascal. Kuntal. Hi, Kuntal. Hi, Remus. Hi, Raluca.
Yeah.
Hello, hello.
Hi.
Hello, Sabia. Hello, Lasse.
Hello.
Hello, Pascal. Bonjour, Pascal. Hello, Kuntal. Hello, Walter.
Okay, so if there are no more questions from here or from there, let's thank the speaker again.